This last lesson of linear programming is probably the more challenging one of the 8. In the POTS example, we solved for the intersection point using graphics calculator and Desmos. We can, however, do this completely algebraically if we don't have a computer like we do in an exam, and suppose I've forgotten our calculator, using theory of simultaneous equations. We're trying to find the intersection point of these two inequalities. I've used S's and L's instead of X's and Y's, okay, because I know that I'm not using technology, so it doesn't matter. And I'm trying to find this intersection point at 8, 2. There's a few different methods that we can use to go about these. Substitution method would be quite a suitable one here. I'll rewrite these two inequations as equations. So changing the less than or equal sign to an equal sign. This is equation 1 and this is equation 2. I can rearrange equation 1 to get one of these variables by themselves. In this case, I'll get S by itself. And now what I'm going to do is substitute S equals 10 minus L into equation 2. Which means where I see this S here in equation 2, I'm instead going to write 10 minus L. So what it ends up looking like is 10 minus L plus 2L equals 12. Good thing about this is that now I've only got one variable which I can now rearrange and solve. So I can bring the 10 to the other side. Minus L plus 2L equals 12 minus 10. Minus 1 plus 2 is really 1, so this is just L, and L equals 2. So I found my L coordinate, or I think in this case it's my X coordinate. Correction, my Y coordinate. I've drawn it for large and small. I need to be able to find the S as well. So to find S, I'm going to substitute L equals 2 into something that'll find what S is. That looks like a pretty good equation that'll find what S is. S equals 10 minus, instead of writing L, I'll write 2. S equals 8. And there's my solution. L equals 2, S equals 8. I should probably check this to make sure that it works. So in equation 1, I'm going to substitute S equals 8 and L equals 2 and make sure it equals 10. So 8 plus 2 equals 10, all good. And check in equation 2, 8 plus 2 times 2 equals 12, is that correct? Yep, all good. 8 plus 4 is 12. Okay, so I know that that is my intersection point, and from there I would be evaluating the objective function at that point. There is an alternate method to solving this called the elimination method. So again, I would write my two equations side by side. I'm again trying to find this intersection point. In this case, I'm going to notice that these S's both have a coefficient or number beside them of 1. So what I can do is take, say, equation 1 and subtract equation 2. So I'm going to be subtracting the bottom line from the top line. So I'll go down, S minus S gives me nothing, don't need to write anything. L minus 2L will give me negative L, and 10 minus 12 will give me negative 2. I can then divide both sides by minus 1 or multiply by minus 1 and get L equals 2. Okay, from here I still need to find S. So to find S, I'll substitute L equals 2 into equation 1 or 2, either one, doesn't matter, which is S plus L equals 10. I'll do that. S plus 2 equals 10. S equals 10 minus 2. I get S equals 8. Okay, exactly the same as I did above. And if I really want to, I can do the check again. In equation 1, 8 plus 2 equals 10. All good. In equation 2, 8 plus 2 times 2 equals 12. Again, all good. So they're basically the two methods. There are some little variations of elimination method as you go through a few more problems, but that's how we would do it algebraically. There are a few, I guess, more interesting examples. For example, this one where I've got a horizontal line intersecting with a diagonal line, but I can just do the same things that I've done. I'd probably use substitution method here. So y equals 4 would be equation 1, and x plus 2y equals 12 would be equation 2. I'm going to sub y equals 4 into equation 2. So wherever I see y, I'm going to replace it with 4. X plus 2 times 4 equals 12. The x is 12 minus 8. Gives us an x value of 4. Do I need to find the y value? Sure, I could sub x equals 4 into y equals 4, but y would still be 4. Okay, so my solution in terms of xy would be 4, 4. And I could check this. So equation 1, I'm going to substitute y equals 4 in there, so 4 equals 4, which is true. Equation 2, 4 plus 2 times 4 equals 12, is that correct? Yep, all good. So the solution's correct. Just gone back and written the correct solution form in both of those ones on the previous page. Right, the last problem to have a look at is a particularly nasty elimination rule. So again, I've got x's and y's, trying to find this point in here. Looks like I might be able to find it algebraically. Okay, it looks like it's 6, 6. We'll see how we go. So this is really for A++ students. If I was going to try and do substitution on here, either of these equations that I would rearrange, I would get something like y equals 30 minus 3x on 2, and then I'd have to substitute this into here, which would be a nightmare. Okay, it'd get really messy. I can and would prefer to use elimination method in these scenarios. So I'll write down what my two equations are. If I tried to add or subtract these, say I subtracted, I'd end up with x minus y equals 0, which is useless because I've still got those two variables. So if I want to use elimination method here, I need to find some way to target either the x's or the y's and make the number in front of them the same. I'm going to target the y's just for fun. I'm going to try and make both of them equal 6. So I'm going to multiply equation 1 by 3. And I'm going to multiply equation 2 by 2. It's the same method that you'd use trying to find a common factor, a common denominator to add these two. You'd think, okay, needs to be 6, need to multiply the top by 3, and this top by 2. Okay, it's the exact same thought process. So I'll do this multiplication, multiplying every term by 3. 9x plus 6y is 90. That's my new equation 1. And multiply equation 2 by 2. 4x plus 6y equals 60. So now that I've got the y's the same, I can do 3 times equation 1 minus 2 times equation 2. Subtracting down. 9x minus 5x is 5x. 6y minus 6y is nothing. 90 minus 60 is 30. So my x value will be 30 divided by 5, which is really 6. It's starting to look pretty good. I need to find the y value now. So I'm going to substitute x equals 6 into, doesn't matter, either equation 1 or equation 2. I'll choose equation 1, which is 3x plus 2y equals 30. Put the x equals 6 in there. 3 times 6 plus 2y is 30. 18 plus 2y is 30. So 2y is 12. Y equals 6. My solution in terms of xy is 6, 6. And just as I predicted it would be from the graph. I better check that it works for both equations. In equation 1, 3 times 6 plus 2 times 6, is that equal to 30? Sounds good to me. And checking in equation 2, 2 times 6 plus 3 times 6, is that equal to 30? 12 plus 18, yep, that's also 30, all good. So my solution is correct. There's a few more problems down here to have a go at. I want you to have a crack at them. Try and use these algebraic methods if you can, otherwise go back to your either graphing on paper or using the graphics calculator.